This is experiment 4 on building hypersurfaces, 2006 to 2012. The goal for experiment 4 was to use sheet metal to build hypersurfaces, which are here defined as curved 3D surfaces on which 2D tilings projected from higher dimensions are mapped. The tilings are periodic, non-periodic, or irregular. My interest in higher dimensions began in the late 1970s. Looking for ways to build higher dimensional structures led to an interest in their physical realization as projections in 2D and 3D. Shown in the diagram on the right is an orthographic 2D projection of a 7D cube shown in 1/2. You can visualize the full 7D cube by mirroring it. It is centrally symmetric. The outer boundary is a regular 14-sided polygon, in general a 2n-sided polygon for n-dimensional cube. The angle at its center is 360 degrees divided by 14 and is represented by number 1. This is the angle number. All other angles are multiples of this number. Building the 2D projection from physical pieces required breaking the diagram into building blocks, in this case rhombi. The number of possible rhombi from 7D are the only pairs that add up to 7 as shown in the equation. There are only 3 pairs possible, 1, 6, 2, 5, 3, 4. Therefore, there are only 3 possible rhombi from dimension 7. On the left are my original drawings from 1981, which record this discovery. It lists permissible tiles for dimensions 4 through 12 inside each box with the corresponding dimension number on the bottom right. Also in the 1980s, periodic tables of convex and non-convex tiles projected from higher dimensions were developed. The table on left is part of a table of convex zonagons and includes rhombi, hexagons, octagons, and so on, and the table on the right shows non-convex hexagons. Similar tables exist for all other non-convex zonagons. On the right is a reproduction of an illustration of some of these tiles and tilings in an image published in the International Journal of Space Structures in 1986-87. The rule for any of these tilings, periodic, non-periodic, or irregular, is simple. All angle numbers at any vertex equal 2n. The rule for tile shapes is also simple. The sum of interior angle numbers of any tile, convex or non-convex, equals p minus 2 times n, where p is the number of sides of the polygon. These are hand drawings from the period 1981 to 91, all prepared for various patents. Those were pre-digital days when handmade drawings became paste-ups after multiple Xerox reductions. These are all self-tilings. A single tile shape fills the plane. Convex hexagons on the left, non-convex hexagons in the middle, and non-convex octagons on the right. And this process can continue in this manner with higher number of sides. More complex versions, also with self-tilings. You can see the 6, 8, and 10-sided bow ties on the left and the unusual S-shaped tiles in the middle bottom with the number 14. These are 14-sided tiles that fill the plane. Even more curious are the 3 tilings on the right with 16, 18, and 22-sided tiles all covering the plane by themselves. Some of them, like the 22-sided polygons, start to resemble creatures and provide an alternative to Escher's method of making creatures. Since smaller polygons are being fused to make larger polygons, this idea can be continued to polygons with more sides. Finally, the idea extends to 3D space fillings in a similar manner. The most natural analog to these zonagons would be saddle zonohedra composed of saddle zonagons. For each tiling number, you can make a tiling kit comprising convex and non-convex tiles. Shown here is one kit based on the number 5 projected from 5D called pentiles. Similar kits, hextiles, heptiles, octiles, and so on are possible. These are curved surfaces which are tiled with the rhombuses from 4, 5, and 6D cases. The faces of known polyhedra are tiled with rhombi that correspond to the polygonal face, a square with rhombi from 4D, the triangle with rhombi from 6D, the pentagon with Penrose rhombi from 5D, and so on. Asymmetry was achieved by reorienting the face differently from its neighbors. On the right are tiling patterns applied to membranes, bottom right showing a fractal coloring of a fabric pattern. The Milgo experiment was to make these from flat sheets. It essentially meant all rhombi were triangulated into two halves, and triangulated spherical nets were flattened, laser cut, and bent to the correct dihedral angles till they met. This became more challenging with increased size and thickness of metal. It was easy to make ellipsoids from spheres since this triangulation was preserved. You can see two versions, one where the polygons are voids, which are cutouts in the metal sheet, and the other on bottom left, where the polygons are solids and joined point to point. Two examples of spheres are shown here, on the left with solid six-sided crescents with rounded corners, and the one on the right with an assortment of polygons left as voids to make a frame structure. Seat 54 in Midtown Manhattan on 54th Street and 6th Avenue was a commission for the outdoor plaza renovation of the building. It was in quarter-inch thick steel. The cut marks were introduced to enable bending. This was not an easy job to get the bends at the precise dihedral angles, but was achieved on the brake press by an expert metal worker at the factory. Digital models for possible sculptures. They are mapped on two or more rhombohedra, which are 3D projections of a cube in higher dimensions. The faces of rhombohedra are tiled with rhombic tilings. The tiled faces are mapped onto a continuous curved surface by blending the rhombohedra into a smooth surface. Here are shown 3D models of cells of increasing dimensions of a non-periodic minimal surface, the higher dimensional version of the Schwartz surface. It uses the two golden rhombohedra as the building blocks derived from the icosahedron and familiar from the work on quasicrystals. These provide the starting point for the next slide. Sculpture studies from the Hyper-Schwartz surface in the last slide, tiled with n equals 6 rhombi. On left is the triangulated version. In the middle is a rhombic version with elliptical voids. On top right with triangular voids, and bottom right with six-sided crescents as voids. Concluding remarks. Hypersurfaces are part of authors' ongoing interest in realizing high-dimensional architecture, hyperspaces, and hyperstructures. Since our physical space is three-dimensional, high-dimensional structures cannot be built, yet their projections can be. As these experiments show, they are full of rich possibilities for architecture, art, and design, and they may have implications for other fields as well. Personally, I see higher dimensions as solutions that are looking for problems. A lot of people to thank over the years: Bruce Gitlin and the entire Milgo production staff for their continuous support, computer modeling, Neil, John, Peter, Patrick, and Robinson, various other support through the project, and at Pratt Institute, again, everyone for the continuing support over the years. I'm very grateful to everyone. Thank you very much.